Hey everybody, Razcast here again, and this is Unit 4 on the AP Physics syllabus, Energy. Now, I like to think of physics as the study of matter and energy, and so it's understandable that this will be a huge part of the syllabus and the exam, as it is a foundational topic that is going to spiral throughout the rest of the syllabus. In fact, you can even apply energy principles and ideas of energy to solve problems that you may have looked at previously using only forces and dynamics. That said, there are only three subtopics here, and these three big ideas, forces and interactions, the idea of change in a system, and the idea of conservation, are the foundational principles that go throughout this unit. So, open and closed systems. The enduring understanding here is that certain quantities are conserved, and energy is the first one that we're being exposed to in the AP Physics 1 syllabus. Now, conserved, as we'll see, means that these quantities, as you may have heard, are not created or destroyed. So they are always equal in total in the universe. However, there's a difference between a closed system and an open system. And so the essential knowledge for this subtopic is that a system is an object or collection of objects. For all systems, there are certain conserved quantities, and the idea of how we define a system is completely arbitrary and is totally up to the observer, and is usually done in order to simplify things. So, to sum it up, these are the conserved quantities: energy, charge, linear momentum, angular momentum. These quantities are always conserved, meaning they are never created or destroyed. However, they may not be constant within the system that we define. If we define a system which is closed with respect to one of these, it means that the total of this quantity in the system is the same before and after. Whereas if it's open, it means that the amount by which the system changed in this particular quantity is equal and opposite to the amount by which the surroundings changed. To be more specific, for example, with energy, if we have an increase in the energy of the system, it's probably because the surroundings supplied that energy, so there was a decrease from the surroundings. Now, the main objective related to this concept is being able to define open and closed systems and apply conservation concepts as such. And that's about it. Everything else for this idea of open and closed systems is all just foundational knowledge that we'll build upon in the remainder of the course. Work and mechanical energy. So, the definition of work is force by distance in the same direction. Work is also defined as the increase of energy of a system. So work is done on a system when a force is exerted on that system or object in the same direction that that object is moved. Work can also be said to be done on a system when energy is supplied to the system. So the main thing in calculating work done, you can only use the parallel component to the object's motion. Force that is perpendicular to the motion of an object can change the direction of an object, but it's not going to increase its energy. Now, net work is done by a net force, and the net work done on an object is equal to the change in kinetic energy of the object. That's called the work energy principle. So, to find work, in order to determine the amount of work done on an object, you can use this formula if the force is constant. If the force is not constant, then you're going to want to use a graph, and it will be the area below the fx graph, or more specifically the area between the graph and the x-axis. Now, the force that is graphed must be the parallel force to the direction of motion of the object. A negative work means there's been a negative change in the energy of the system. This is done when the force is directed in the opposite direction to the object's motion. So if we take an example of a graph, here we have a graph of force versus distance, assuming that this object was initially at rest or moving in the positive direction. The area that is above the x-axis would represent positive work done on increase in energy of the object, and the area below the x-axis will represent negative work done or a decrease in energy of the object. In order to find that area, we can take part of the triangle area of that trapezoid shape, and if we move it around, we get a rectangle. That rectangle, what I actually did there was I found the average base. Base 1 plus base 2 divided by 2 gives me the average base, multiplied by the height is going to give you the area. That's called the trapezoid rule. Alright, in determining mechanical energy, these are the different types of energy that we deal with at AP Physics 1 level, and these equations are all provided for you. Now keep in mind that usually we calculate delta UG, which is the change in gravitational potential energy with respect to some baseline. So that will be a change in Y with respect to some original starting point. The learning objectives for this one is that you're able to calculate the total energy and justify how you calculated it, as well as predict the change in total energy due to changes in position and speed. So this comes back to being able to calculate the different forms of energy. Now, although thermodynamics is not part of Physics 1, the idea is included of mechanical energy dissipating, meaning being converted to thermal energy when you have inelastic collisions as well as friction. So on to the third subtopic, conservation of energy, and this is where everything is really applied. So first point that the AP Physics syllabus really emphasizes is the idea that a single object can only have kinetic energy. Potential energy requires a conservative force, and a force by definition is an interaction between two objects. Therefore, potential energy can only be possessed by a system of at least two objects. It's a technicality, but it comes up all the time, so it's one that you should be aware of. Now, to apply the principle of conservation of energy in a mathematical sense, I like to sum it up in this simple equation. The total energy before plus any work done on the system, if there has been work done on the system, is equal to the total energy after. Remember that work is defined as being done on a system when the energy is increased. You can do negative work on a system, meaning you take energy away. So if you add the work done on the system to the energy you had before, that will give you the amount of energy after. If no work was done on the system, that system is considered a closed system. The total energy before is equal to the total energy after. Now, total energy, remember, is the sum of all those types of energies. So these are the learning objectives under this subtopic in the syllabus. You need to be able to calculate the expected behavior of a system using an object model, and then when this fails, use conservation of energy to show that the object is actually a system and to explain what happened. So that can sound a bit confusing, but here's a simple example. So if I have this car that has a spring inside it, and I just had it at rest and then released it, the spring flies out, there's a lot of energy that is released. If I were to view this as simply an object, there'd be no explanation for that energy that was just released. If I then view this as a system that has internal structure, that internal structure being a spring, then I can talk about the potential energy of the spring plunger system within this car, and then that makes sense. Okay, describe and make predictions about the internal energy of systems, calculate changes in kinetic energy and potential energy, design an experiment to do a couple things related to energy, and predict and calculate energy transfer or work done based on graphical data, then make claims about the interaction between a system and its environment, and predict and calculate energy transfer related to a force exerted on a system through a distance. So it's all just summed up in that equation here. So let's look at the problem solving strategy for energy questions. It's all going to come down to conservation of energy. And so keep this equation in mind. Total energy before plus work done on the system is going to be equal to your total energy after. And how we apply this is just by asking a series of questions. Start with the energy before and you ask, is it moving? If yes, then you calculate the translational kinetic energy. Is it spinning? That will give you rotational kinetic energy. Is there a spring that's compressed? Spring potential energy. Is it raised a height above some baseline? That will give you gravitational potential energy. You sum all of those up and you have your total energy before. Then you ask yourself, can I draw a free body diagram of this object or system? Is there a net force? If there is, that implies that work is going to be done on the system. If not, there's no work done on the system. It should be conserved. The total before should be equal to the total after. If there is a net force, is it in the same direction as the motion of the object or system, or is it opposing it? That will tell you whether that work is going to be positive or negative. But whether that work is positive or negative, you're still going to add it to the energy before. So if you add a negative number, it means obviously you subtract that quantity. Remember that you have to use the parallel force multiplied by the distance if it's a constant force, or you can use a graph if it's a variable force. Next, we move on to the total energy after. You ask those same questions that you asked before, and you sum it up. And finally, you equate both sides. If you find that there's any missing or unaccounted for energy, then this implies that some energy was either gained by or lost from the system, and that would have either been coming from or lost to the surroundings, most commonly dissipated as heat due to friction or sometimes in an inelastic collision. Other possibilities would be in sound when there's a collision as well, and also in internal energy when there's deformation. These are the most common examples of how energy is dissipated to the surroundings, at least at this AP Physics 1 level. So I hope that gave you a good understanding of these big ideas and how they apply to this really foundational principle and huge part of the AP Physics 1 exam. I strongly suggest you look at past exam questions and solutions. They're available online at this link, and these are the 3 that are most relevant to this topic. So with that, I hope you have fun, because physics is fun.